Every day, thousands of Airbus aircraft take off and land all over the world, in total safety for passengers, freight, and of course the crews. However, because not all flights are ever quite the same, unexpected and rare events may happen, requiring a calm recovery reaction from the crew. The stall is one of these unexpected events. Here the crew must fully understand what is going on to be able to adapt and control the situation, with one sole aim: recover the aircraft. So it is possible to recover an Airbus from a stall situation. Over and above the currently published documents that resulted from collaborative work between aircraft manufacturers and air safety organizations, we would like to go further in explaining the characteristics of the stall phenomenon, and specifically how to recover from a stall. For all pilots, the top priority is to clearly identify an approaching stall, so that the stall itself can be avoided. However, should one be encountered, then the correct recovery actions must be taken immediately. A stall is characterized by a loss of control, then by a loss of height. A wing generates lift, where L equals a half rho V squared SCL. The lift must equal the weight of the aircraft times the load factor. L equals N times W. N equals load factor, W equals weight. The general lift equation becomes N times W equals L equals a half rho V squared SCL. The CL of the wing increases with the angle of attack up to a maximum CL max. Any further increase of angle of attack above this angle of attack of CL max will make it impossible for the airflow to smoothly follow the upper wing surface. The flow will separate from the surface, causing the CL to decrease and drag to increase. On this graph, we can clearly see that the angle of attack increases from zero lift value. The curve is linear over a big range. When the flow separation begins, the slope of the curve begins to fall off. The lift reaches a maximum and begins to decrease. The angle of attack at which it starts to decrease is the stalling angle of attack or critical angle of attack. This corresponds to the value of CL max. One can clearly notice that to recover from a stall or to prevent a stall, the angle of attack must be decreased to below this CL max value. The aircraft is considered stalled when the behavior of the aircraft gives the pilot a clear and distinctive indication that the aircraft is stalled. Indications of a stall, occurring either individually or in a combination, are a nose-down pitch that cannot be readily arrested, buffeting of a magnitude and severity that it becomes a strong and effective deterrent to further speed reduction. The pitch control reaches the aft stop, and it is impossible to stop the aircraft from descending. Stall characteristics vary with different types of aircraft. However, for modern aircraft during most normal maneuvers, the onset of the stall is gradual. The first indications of an approaching stall may be provided by any or all of the following: unresponsive flight controls, a stall warning or stall prevention device, significant uncommanded roll at the stall, or aerodynamic buffeting. The transition from approaching stall to stall is sometimes difficult to identify precisely. Therefore, the two phases should be treated as the same from a recovery point of view. Factors that affect the stall speed are change in weight, maneuvering the aircraft increasing the load factor, configuration changes. This is how the CL versus angle of attack changes with slats extension, flaps extension, speed brakes extension, and finally wing contamination. Let's see how the CL max varies with the Mach. Remember the general lift equation, N times W equals L equals a half rho V squared SCL. Expressed in Mach condition, it becomes N times W equals L equals 0.7 p Mach squared SCL. At a low Mach number for a given configuration, a wing stalls at a given angle of attack. Beyond a given Mach number, order of magnitude Mach 0.35, any Mach number increase has two consequences. The angle of attack at which the wing stalls decreases. The maximum lift coefficient, which is obtained at stall angle of attack, decreases as well. It means that at high altitude, where Mach effects become significant, the margin from the stall decreases. In other words, in a high-altitude cruise, when the Mach number increases, the lift capacity decreases. That is to say, the load factor capability decreases, as does the ability to maneuver. That being said, let's now take a look at particular stall phenomena. Accelerated stall. An accelerated stall is caused by abrupt or excessive control movement. An accelerated stall can occur during a sudden change in flight path, during maneuvers such as steep turns or a rapid recovery from a dive. It is called accelerated stall because it occurs at a load factor greater than 1g. Secondary stall. A secondary stall may be triggered while attempting to recover from a stall. This usually happens as a result of trying to hasten the stall recovery, either by not decreasing the angle of attack enough at stall recognition stall warning, or by not allowing sufficient time for the aircraft to begin flying again before attempting to regain altitude loss. Pitch up effect. The shape of the wing will also determine the stall characteristics. Modern jet aircraft have swept back wings. This kind of wing allows higher speed, but it has an increased tendency to stall at or near the wingtip first. The loss of lift at the wingtip moves the center of pressure forward, thus inducing a pitch-up moment. So, what do we have to remember? For a given Mach number, a wing stalls at a given angle of attack. When the Mach number increases, the value of angle of attack stall decreases. When approaching the angle of attack stall, the wing generates a certain level of buffeting, which tends to increase at a high Mach number. When the angle of attack increases and approaches the angle of attack stall, in certain cases, a phenomenon of pitch up occurs as a result of the change in lift distribution on the wing. When the flow over the wing is stalled, the only possible means to recover a normal flow is to decrease the angle of attack to a value lower than the angle of attack stall. Stall is only an angle of attack problem. It is not directly a speed problem. Remember these last 2 points. So, that's the theory. But how does it work in practice? For this, we've decided to use a production A330, representative of aircraft in service. Let's start with deterrent buffet. Deterrent buffet is a phenomenon which happens at a certain stage in a stall. It is so strong that it can be dissuasive. It should be noted that the definition of deterrent buffet is part of the stall definition as specified in documents certified by the civil aviation authorities. Buffeting starts gently and gradually increases until the pilots decide to recover. Note that buffeting is hardly perceptible at all when the warning is triggered, but builds up quite quickly to a very harsh level.
Stall, stall. Stall, stall. Stall, stall. Stall, stall. Stall, stall.
Let's focus now on the recovery. In this shot, we have inserted a cross symbol to represent the stick. When the stick is pulled backwards, the cross moves to the nose up position. When the stick is pushed forwards, the cross moves to the nose down position. You can now observe that during the whole recovery, we made a nose down input. We can therefore deduce that deterrent buffet is directly associated with the turbulent airflow, wing stalled condition, and that it disappears when the stick is pushed forward and the flow reattaches. In this graph, you can see the angle of attack at which the stall warning will start in function of the Mach number. You can note that the stall warning angle of attack decreases as the Mach increases. There is also the curve showing the buffet onset. The zone above the stall curve is the deterrent buffet zone. You can see that as the angle of attack increases, we enter the different zones on the graph. Once the recovery is initiated, this deterrent buffet stops. You may also notice that the sudden change in angle of attack occurs as soon as the recovery procedure is applied. Let's review this again.
Stall, stall. Stall, stall. Stall, stall. Stall, stall. Stall.
In the event of a significant uncommanded roll at the stall, reduce angle of attack before recovering the bank angle. In this film, you have seen various theoretical and practical aspects of stall situations. The most important thing to remember is that at the first indication of a stall, you must release the back pressure and, if necessary, push the stick forward to decrease the angle of attack until the stall indications are no longer present. Remember, it is always better to avoid a stall, but should you encounter one, strictly apply the recovery procedures published in your aircraft operations manual.